Hi, I'm Professor Chris Stokes from the Geography Department at Durham University. Where did I start as a researcher? Well, I grew up in South Manchester, just south of Stockport on the edge of the Peak District, and I'd always been interested in geography and the landscapes around me. So you could argue amongst playing lots of football as a child, I was always very interested in how landscapes form, and geography was my favourite subject. So I ended up doing geography for A level. I then did geography for degree level, and I remember taking some time out in the summer between my second and third year as an undergraduate, and actually going to see a glacier for the first time in Sweden. And I was just amazed at these giant masses of ice that were creaking. There was water dripping, there was sounds, there was noises, and it almost felt like it was a living being. And it really just attracted me to that area of research. So I remember then studying final year modules in glaciology and climate and reconstructing past climates. And then I ended up doing a PhD at Sheffield as well, looking at reconstructing past ice sheets. And after that PhD, I then started as a lecturer at Reading University. So that was obviously a highlight, getting your first job and being able to see glaciers around the world as part of your job was just a fascinating thing. I moved to Durham in 2007. Obviously, that was a highlight, coming here to one of the largest kind of groups of glacial researchers in the UK. And since then, I've been doing research over the last 20 years or so, almost 20 years now, on glaciers and climate change. The main kind of thrust of my research is on glaciers and climate change, and most of my early work following my PhD was about reconstructing past ice sheet dynamics and looking at how they changed over timescales of kind of hundreds to thousands of years. But over the last 10 years or so, my research has mostly kind of refocused on modern day glaciology. So looking at how small mountain glaciers and large ice sheets have been responding to climate change over the last few decades. And most recently, we've also been looking at how they might respond to future climate change. And one of the kind of main motivations for this is that we know that glaciers are contributing to sea level, and we know that this is going to be a major problem, not just for countries that have got a coastline, but also for countries, even landlocked countries who might feel the impacts indirectly through, for example, migration and people having to move from coastal areas in the future. In terms of challenges, I think I'd kind of break them down into two parts. I think just, in terms of personal challenges, as somebody who, grew up, in the outskirts of Greater Manchester, and I remember being told, don't bother even applying to Durham University because you won't get in. And all of a sudden, I'm kind of working here now, and I think a lot of academics talk about the kind of imposter syndrome of kind of finding yourself in this place and feeling like you're a bit of an imposter and you don't deserve to be here, or you don't have the skills to be here. So that's always been a kind of lingering challenge that I think a lot of academics will feel. I think scientifically, there's also been a number of challenges of working in kind of climate change. I can remember, in the past giving public lectures and even talks to undergraduates, and there's been a bit of skepticism around climate change. And I think one of the great things is that the scientific evidence, the consensus, has now reached a point where it's very hard to deny that climate change is taking place. But a particular challenge is now some of the financial arguments, which are equally flawed as some of the scientific falsehoods that were being spouted around. Some of the lines that are being spouted that it'll cost jobs, it'll cost livelihoods if we try and adapt to climate change. It's nonsense. We know that in the long term, mitigating now will save us money in the long run. So I still find it frustrating that there are some kind of, shall we say, less than genuine websites and social media platforms who are quite outspoken in terms of climate change. And I do find that a challenge, especially when you're somebody who's trying to work with a little bit of policy engagement, and I can say a bit more about that. But certainly, there's a lot of noise still around climate change, and it can be unhelpful when arguments are put out there that are simply untrue. And so I do find that a challenge, spending time, you could argue wasting time trying to counter some of those arguments, which are distracting from the main thing, which is to kind of decarbonise as quickly as possible. In terms of what's motivated me to do the research that I do, I think certainly early on there was just a kind of intellectual curiosity. I was interested in landforms and landscapes and how they formed. And then as my research focus has changed more towards kind of looking at contemporary glacier change and sea level rise, there's a real motivation there. This is one of the kind of grand challenges that kind of the globe is facing at the moment, climate change, and probably one of the most hard-hitting and impactful results of climate change will be sea level rise. I mean, if we think that, I think it's about 230 million people live within 1 metre of sea level, and we know that 1 metre of sea level is perhaps possible as early as 2100. So within the lifetime of some of our children, they're going to experience that sea level rise, and that's going to involve huge amount of displacement for people. And so one of the kind of key motivations for my research at the moment is trying to convey to policymakers, climate negotiators, for example, at COPs, the Conference of the Parties, which takes place every year, to try and give them up-to-date information about how the choices they make now will have impacts, and potentially some of those impacts will be irreversible. So, for example, if we think of the Paris Climate Agreement, which aimed to limit warming to 2 degrees, but ideally to 1.5 degrees, well, we're at 1.2 degrees now above pre-industrial, so we've got 0.3 of a degree to go, if you like. Although I should emphasise it's not a target we're trying to hit. But one of the messages that we've been conveying, and something which our own research shows, is that once you exceed 1.5 degrees, you actually start seeing some quite dramatic changes in the world's ice sheets in Greenland and in Antarctica. And once you go past 1.5 degrees, we start to move into what we call irreversible territory, where once we've gone past that threshold, even if we cool temperatures again, it will be too late, essentially, over the next few centuries. We'll be then committed to further sea level rise. So one of the main motivations for my research at the moment is bringing the latest science into some of the negotiations at things like the Conference of the Parties, the COPs, most recently in Dubai, of course, really trying to press home that the science is saying that we must do all we can to limit warming to 1.5 degrees. I can think of several significant developments in my field over the last 2 decades. I can still remember studying ice sheets like Greenland and Antarctica, and as an undergraduate, and I was being taught that these huge masses of ice will take centuries to respond to climate change. And certainly within the last 2 decades, our knowledge of how quickly those big ice masses can change has just undergone a huge paradigm shift. We now know that there are very dramatic changes happening in Greenland and Antarctica, which are contributing to a very rapid rise in sea level, which appears to be accelerating. So that's one development. I think we now understand that we could see quite dramatic changes in the big ice sheets in Greenland and Antarctica. I think the other major development, it's been more of a technological advance, is satellite remote sensing. A lot of the data that I use in my research uses satellite observations. So there are literally hundreds of satellites orbiting the Earth, and they're imaging different things on the Earth's surface. And I can remember in my PhD, we had to spend about £1,000 to buy one satellite image. And I now have dissertation students on our undergraduate programs mapping from thousands of them, and they're all free of charge and publicly available. So there's been a huge change in not only the number of satellite sensors available to detect changes in ice sheets, but also they've become freely available. There's been a huge amount of data to access, which have really improved our understanding of some of the changes taking place in Antarctica and Greenland. So that's just been a huge change in the kind of our ability to detect what is going on. We have satellites now that effectively can measure to the nearest millimetre the drop in elevation of Antarctica every 10 days, every 2 weeks. So we've almost got too much data. I think the next major development will need to be in our ability to simulate these changes and future changes using computer models. I think if we look at how climate science has progressed over the years, with the ever increasing computational power that we can run really sophisticated projections of climate and weather, we really need to be able to do that for ice sheets so we can better constrain what the rate of sea level rise will be over the next few decades and few centuries. Most recently, we've been doing research here in the geography department focused on the world's largest ice sheet in East Antarctica. So Antarctica is generally divided into two parts, the West Antarctic ice sheet and the East Antarctic ice sheet. And East Antarctica contains about 52 metres of sea level equivalent. So if you melted all the ice, sea level would rise by 52 metres. West Antarctica is actually an order of magnitude smaller, less than 5 metres of sea level equivalent. And I've always found it interesting that people have kind of neglected the East Antarctic ice sheet. We've often thought it's so big, it's so cold, it's so remote, we're not really expecting it to be very sensitive to climate change. And over the last few years, I've had a series of master students and PhD students and postdocs as well, looking at the stability of the East Antarctic ice sheet. And what's become really clear is that this kind of sleeping giant of climate change appears to be waking up. So we've been doing a lot of research showing that there are some quite dramatic changes taking place in East Antarctica that are actually very similar to those taking place in West Antarctica. Now, West Antarctica has been contributing to sea level rise for the last couple of decades, and we're starting to see now the emerging signs of similar processes happening in East Antarctica. And so we're thinking that, the threshold for this ice sheet to start responding to climate change is very, very close if we haven't already passed it. I can remember reading papers in the late 1990s saying it would take 15 degrees of warming for anything to happen in East Antarctica. Well, we've warmed at about 1.2 degrees, and we're starting to see the oceans warm up there. We're starting to see ice shelves collapse. We're starting to see glaciers retreating and thinning and contributing to sea level rise. So a major focus of our research is to keep monitoring this very large ice sheet in East Antarctica and try and better understand the processes that might lead it to contribute quite rapid rates of sea level rise in the future. A lot of the work that I do on glaciers and ice sheets and the fact that they're melting and contributing to sea level rise is actually directly relevant to some of the negotiations that take place within the United Nations Framework Convention on Climate Change. And so the kind of the pinnacle of the UNFCCC, as they call it, are the Conference of the Parties, which take place once a year. And I've been very lucky to attend the last two COPs as an observer, because Durham University has observer status. And what we tend to do at those COPs, together with a small number of scientists from around the world, is that we work with an organisation, a non-governmental organisation called the International Cryosphere Climate Initiative, and they connect scientists with policymakers, particularly at COPs, but also outside of COPs as well. And we work with countries, climate negotiators, policymakers from different parts of the world, but particularly those that have a vested interest, for example, in sea level rise. So if we think of the alliance of small island states and those Pacific islands that might be most vulnerable to sea level rise, well, they obviously need the most up-to-date science and projections around sea level rise to take in to the negotiations. So although as an observer and a scientist, I don't get to participate in the negotiations, we can sit in on those, but we can also speak to climate negotiators, we can speak to policymakers, and we can give them the information that they need to make better decisions and to feed the science into the various negotiation tracks. And we have seen some kind of tangible benefits of this over the last two COPs, where cryosphere so that the Earth's icy environment. So it has started to move up the agenda, and it's being used particularly to stress the importance of limiting warming to 1.5 degrees, because we know when we exceed 1.5 degrees, we start to see some irreversible impacts, both on ice sheets, but also in terms of Arctic sea ice, in terms of permafrost, mountain glaciers and water resources. Once we go past about 1.5 degrees, we start to see some really, really dramatic changes. So it's been great over the last couple of years to work a little bit more at the kind of science policy interface and engage with some of those processes and feed in our research from Durham, but also the research that other workers are doing into those negotiations that take place at quite a high level at venues such as the COPs. Over the last few years, we've been doing a lot of work monitoring and taking observations of how the ice sheets are changing in places like Greenland and Antarctica, particularly East Antarctica. And we've got a really good handle now on the observed changes in these ice sheets. And so in terms of future directions for my research and our research in the department here in this particular topic, I think one of the things that we need to do much better, and I speak for the whole community here, not just for people in Durham, is actually project the future changes. So we have lots of observations. Arguably, we've got as many observations as we need now. But what we still need to improve on is our projections of future changes. So, we can run computer simulations, we can use various emissions trajectories and climate warming trajectories, and we start to see changes in the ice sheets, but there's still quite large uncertainties, particularly around how the ocean, for example, around Antarctica might warm up and how that might impact on the ice sheet dynamics. So I think one of the things that I'd like to work on over the next few years would be kind of improving numerical modelling of ice sheets, perhaps using some of our observations as almost like training data or calibration data, and then working with numerical modelers to improve their projections, but also working with oceanographers as well, so that we can use their data of, say, ocean temperatures and how quickly they're changing to feed into some of the numerical modelling that we're doing. We've also got other projects, for example, that are spinning out from our work in Antarctica. One of those that's quite exciting is a new project that's been funded to look at how emperor penguins are being affected by changes in the ice sheet in Antarctica. So we know bits of the ice are breaking off and contributing to sea level rise. Much less work has been done, for example, on how that's affecting some of the kind of keystone species in places like Antarctica, such as emperor penguins. So we've got a project that will be running over the next 3 years looking at how emperor penguins have responded to past changes in the ice scape, changes in the ice sheet, and how they might respond in the future. And there's lots of other smaller projects that will be ongoing around kind of ice sheet hydrology. We're particularly worried that parts of Antarctica that never used to melt might start to experience quite high levels of melting in the future, and that might lead to processes that cause rapid retreat and collapse of ice shelves. So there's lots to keep us busy on, and of course I'm also hoping to stay involved in some of the policy engagement that we've been doing at the COPs as well. It's fantastic to work in the geography department at Durham. We're a very large department and we have expertise that spans the whole range of physical and human geography. So that's really exciting that you can always lean on colleagues who are just outside of your area of expertise. But also one of the great things is that this department has one of the biggest groups of researchers who are looking at kind of ice, sea level, climate across a range of timescales, both past, present and future. And even if we just think of people working on Antarctica, we've probably got one of the largest groups of Antarctic researchers anywhere outside of the British Antarctic Survey. So it's a really stimulating research environment, and there's lots of colleagues who I also count as friends, many of them as well. And it's great to be able to work with friends and colleagues on problems together. So, very rarely in physical geography do we work alone, we work in teams. And it's been great to work with wonderful colleagues over the years in Durham. And those colleagues include masters, PhD students, postdoctoral fellows. They're the people who are often at the forefront of the discipline, and they're the pioneers who are driving change, moving into new areas, discovering new things. And I find that kind of, that's a really rewarding part of my job, is working with those people.